Hello everyone. In this video, we're going to go over section 5.1's in sequence. So what are sequences? So a sequence is just a collection of objects, usually it's going to be numbers, in which you have repetitions allowed and the order is going to matter. So in general, you represent sequences as a list, and that list is index. You have an index. So for example, you see here I have A1, A2, A3, A4, and we go up to AN. The index is determining the order in which we're representing the terms. Each of the individual elements here is going to be called the term. A1 is the first term, AN is going to be the end term, and once again, N is going to be called the index or the subscript of the sequence. Now, one simple example of that would be the sequence 1, 2, 3, 4, 5, 6. Another sequence will be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. The difference here from sets are because order is going to matter. So 1 to 3 is not the same as 3 to 1. Those are different sequences. Repetitions are allowed here. 1, 1, 2, 2 is a valid sequence. And instead, the repetitions are not allowed because you know that they're going to mean the same thing. So if you compare with sets, the set 1 to 3 is a set equal to the set 3 to 1. And there's no repetition in there that is allowed. So that's the key difference with sets. Now, sequences have also something that is an explicit formula that governs their terms. So for example, we can give the end term directly as a function. So you can consider the end term to be a function of n for all integers. And we got to give a specific starting value. So we always said n is going to be bigger than certain starting value. For example, consider ak equals k for all integers k bigger than 1. Notice that here we given the relationship, we're saying ak, the k term, is given by the k number. And we're going to go with k being bigger or equal than 1. So that means that if we compute the first 4 terms, we will have that a1 is just 1, a2 is 2, a3 is 3, and a4 is 4. Notice that you're replacing the index in the function that we have over here. So because the index was 1, then we have that the output's going to be 1. When the index is 2, then we have that the index, the number is 2, and so on and so forth. Now, this produces the sequence 1, 2, 3, 4, which is, this is a simple example. But now, let's take a look at a more complex sequence. So we have b of k equals k squared over k plus k. So the presentation of this is a little weird, but this is a very valid sequence. You can obviously simplify expressions, but this is just to see how k can be plugged to obtain the values. So for example, if I do b of 1, my index is 1, my k is 1, so I'm going to replace that here, and so it becomes 1 squared over 1 plus 1. So it becomes 1/2. If I do b of 2, that's going to be 2 squared over 2 plus 2, which is like 4 over 4, which is equals 1. b3 will be 3 squared over 3 plus 3, will be 9 over 6, which I can simplify to 3/2. And b of 4, I plug in 4 here, and I get 4 squared over 4 plus 4, which is 16 divided a, which is 2. Now, the sequence here will be 1/2, 1, 3/2, 2. Now, we can have a sequence where we're going to jump between positive and negative number. Consider this sequence here, c of j equals -1 to the j over 3 to the j for j bigger than 0. So our first term is going to be C0, obviously, since we're going to start from 0. And we're going to get that this is the first term is minus 1 to the 0 over 3 to the 0. Plug in that 0 from the index. And so we're going to get that C0 is 1. Now, C of 1 will be minus 1 to the 1 over 3 to the 1. So minus 1 to the 1 is just minus 1. And so we're going to get that this is minus 1/3. C of 2 will be minus 1 squared over 3 squared, which is going to give me 1 over 9. And so on, minus 1 to the 3 over 3 to the 3 is going to give me minus 1 over 27. So this gives me the first 4 terms for this, and it will be 1 minus 1/3, 1, 9, minus 1 over 27. Notice that this minus 1 to the j is something that makes the signs of the term alternate. First it was positive, then negative, then positive, then negative. So remember, the minus 1 to the j is always going to create an alternating sign pattern. Now let's talk about finding explicit formulas. So this when we have a sequence, we can always look for patterns in the sequence of terms. So for example, we have 1 minus 1, 1 minus 1. You kind of see that it's alternating between 1 and minus 1. And you can kind of guess that it's going to be some sort of, minus 1 to the n or minus 1 to the n plus 1. It all depends on where you start. Here, because we start with a positive, if we have that this sequence is starting from 1, from the number 1, you need that the first term is positive. So for that, it gotta be an even number here, minus 1 to an even number. So that's why we have, if we start from 1, we're going to do n plus 1 here. So it's minus 1 squared, which is 1. Then minus 1 to the 2 plus 1, which is minus 1 to the cube, minus 1, so on and so forth. So now you can see the way that we're applying the index, and you can see how some of these variations work. Now, minus 1 to the n plus 1 is not the only way that I can define that. I could also do minus 1 to the n minus 1, but I will have to start from a different point. I will have to start from n equals 1. And so with the exponent, now it will start from 0 instead. So this will be minus 1 to the 0, which will be 1. Then when nx equals 2, minus 1 to the 2 minus 1 will become minus 1, and so on. So you always want to make sure that you're getting the number that you're supposed to get. Now, let's see another example here. So let's find an explicit formula for minus 1, 2, minus 3, 4, minus 5. Notice that we have 1, 2, 3, 4, 5. So we can kind of think that this is an n. A of n is just n. It will start from 1. But then, because we have alternating, then we got to just make sure that the signs start alternating with a negative. So the magnitude is just 1, 2, 3, 4, 5, so just n. And so if we want to make it so when we start from 1, this produces a negative, then we should go with minus 1 power to the n. And that way, when n is equals 1, I get the negative. And so minus 1 times 1, minus 1. When n is equals 2, I get 1 times 2. When it's 3, I get minus 1 to the 3, which is minus 1 times 3, so on and so forth. Okay, so hopefully that gives you an idea how to form patterns. Now let's talk about the next step. We will be, when we have sequences, we can also have series. And the series, they use something that is called the summation, or the sum notation. So if n and n are integers with m less than n, then the symbol sum from k equals m to n of ak means that you're going to add the terms of the sequence from the m term to the n term. So the components of this is the sigma is a summation symbol. This is a capital Greek sigma. K is going to be, of course, the index of summation. M is the lower limit, and n is the upper limit. And ak is the general term that is going to be used, or is going to be sum here. Now, let's make an example here. So we're going to have the sum from k equals 1 to 4 of k squared. So pretty much this is the sum of the first 4 squares. So we have 1 square plus 2 square plus 3 square plus 4 square. So that's what we're doing with this. We're representing the sum of the first 4 square. Now this is going to produce a number as long as we have finite sum, of course. So we have 1 plus 4 plus 9 plus 16, which is going to be 30. Another example here, let's do summation from 0 to 3 from 2 to the I. And so we apply the index 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. Once again, we're adding 4 terms and we're adding powers of 2. So we have 2 to the 0, which is 1, 2 to the 1, that is 2, 2 to the 2, that is 4, 2 to the 3, that is 8. And the total sum here is 15. Last, let's see something different, like sum from j equals 2 to 5 of 2j plus 1. So notice that we're starting at 2. So this is the first term is going to be 2 times 2 plus 1. Then we go with 2 times 3 plus 1, 2 plus 4 times 1 plus 1, and 2 plus 5, 2 times 5 plus 1. And so that once that I have this set up from just the particular term that I'm adding, I can translate this to numbers. This will be 5, 7, 9, and 11. Total sum 32 here. Now, in the same way that we have sum of sequences, we can also have products. So with the product notation, it's going to be more or less the same idea. With m less than n, the symbol multiplication from k equals m to n of ak means that you're just multiplying the numbers from the point m to the point n. And so this will be am times am plus 1 times am plus 2 up to an. So here, this capital Greek letter pi is going to be the product symbol. And we have the same index structure as in the summation. Now, some examples of this will be the multiplication of the first 4 squares, or the multiplication of the first, from the numbers from 2 to 5. So here in the first 4 square, we have 1 squares times 2 squares times 3 squares times 4 squares. And here we have 2 times 3 times 4 times 5. So very straightforward. Okay, so now with this, we can define some properties, and we can also define one of the more used sequences, which is going to be the factorial. So for any real number n bigger than m, we're going to have that the sums work with distribution. So if you have distribution over addition. So if you have the sum of the ak terms from m to n, and the sum of from m to n of b of k, you can consider this like a single sum of both the sum of both of these terms or these sequences. Also, if you have a sum, then you can just do the multiplication of the constant over each of the terms of the sum. So pretty much if you're adding n numbers, you're going to distribute this constant over the n numbers. The product property is mostly about association. So if you have a product from k equals m to n of a sequence ak, multiply the product of another sequence bk from k equals m to n, then you can just simply see that as a single product where you're doing the product from k equals m to n of ak times bk. Now, given that, we can define the factorial quantity. So the factorial quantity is denoted as n and then admiration sign. This is how it's going to look in your calculators or online if you're trying to find out how to calculate a factorial. And it's just a multiplication from 1 up to the number n. So you can see it here backwards, n times n minus 1 times n minus 2 up to 1. But really, that's just the multiplication from 1 to n. We have a special case in this definition, and is that the 0 factorial, we're going to define it as 1, but that's just going to be the initial case. Some examples of factorials are going to be 1 factorial, which is equals 1, 2 factorial, which is 2 times 1, which is 2, 3 factorial, which is 3 times 2 times 1, which is 6, 4 factorial, which is 4 times 3 times 2 times 1, being 24, and 5 factorial, 5 by 4 by 3 by 2 by 1, which is going to be 120. It really grows fast. Okay, so you can do some arithmetics with this. You can compute things like 9 factorial over 7 factorial. And you can have that 9 factorial. If we have common stuff, like for example, we can see 9 factorial is 9 times 8 times 7. And because we can keep multiplying down, we can just see this as 7 factorial. And we're going to cancel out with 7 factorial. So we can cancel this out, and 9 factorial over 7 factorial is just going to give me the remainder numbers, 9 and 8. If you compute things that are a little bit more complex, like 6 factorial over 2 factorial, then you can do multiple things. For example, we can see 6 factorial, that's 6 times 5 times 4 factorial, and then cancel out with the 4 factorial. 2 factorial is just going to be 2 times 1, so it's much more simple to see as 2. And so 6 by 5 is 30, divided by 2, that'll be 15. Now, in general, a shortcut will be if you have n factorial over n minus k factorial, you can see that's n times n minus 1 up to n minus k plus 1, or the first k factors of n factorial. Now, one last thing that we can introduce here is the concept of telescoping sums. And is essentially, just for example, let's say that you're saying compute from k equals 1 to 20 of 1 over k minus 1 over k plus 1. So if you start writing the terms, notice that you're going to get 1 minus 1 half when k equals 1. When k equals 2, you're going to have 1 half minus 1 third. When k equals 3, you're going to have 1 third minus 1 over 4. And then so on. Let's say we get to 20, we get 120 minus 1 over 21. Notice that we have a bunch of repeated terms that they can cancel each other. So this 1 half cancels with this 1 half, this 1 term with this 1 term, so on and so forth. And so what ends up happening with this type of sum is that it's going to give me the initial term minus the last term. And so you can very quickly find what is the sum of all these numbers, computed in the first minus the last term. So most of the terms cancel, and only the first and the last part remains. This is called a telescopic sums because it collapses like a telescope. Okay. All right. So now that we gave that example, I'm going to probably do some more on the class note examples, but let's do a summary of the things that we learned. So we learned sequences, the order list with repetition is allowed, order matters. We have some explicit formula that we can use to calculate. And once that we have that, we can have summation notation, product notation, and things like the factorial that are special sequences that give me the multiplication from 1 to the number n. Telescopic sums, which is where most terms cancels, and we're going to get the final sum being in terms of the first and the last term. Okay, so this is, we're reaching the end of this section. You got to be careful here with not confusing sequences with sets. Starting with index errors, you got to make sure if you're starting at 0 or at 1, and be careful with factorials, not to mistake 0 factorial with 0 or n factorial with n minus 1 factorial with n factorial minus 1. Things like that. Alternating formulas, the 1 minus 1, 1 minus 1. You got to be very careful on checking where it starts and making sure that you're getting the right number with the right index. Okay. All right. So here's the end of section 5.1. We're going to go for some examples, and next we're going to do mathematical induction.